Hello everybody, welcome back to EE368. Today we'll be discussing transfer functions. So what is a transfer function? Well, consider a filter. There we have some input and some output. And we will denote a arbitrary transfer function as h of dot. So h of dot will take the form of this output that we observe over the input. And before we go any further, I first want to define something called passband. And this is where a filter will accept a signal. Okay. And typically, in the case of electronic filters, we have an idea of a 3 dB or cutoff frequency. And this is going to consider some frequency. And here we are going to have the magnitude of, say, h of omega in decibels. So this will be a decibel scale. So consider a low pass filter, like this, like that. We are filtering the high frequencies and accepting or passing through the lower frequencies, right? So where we have the maximum value of our magnitude response and go down 3 decibels, 3 dB, this point, once we've gone down 3 decibels from the maximum transfer, this is called the cutoff frequency, or omega c in this case, since our dependent axis is omega. All right. So this right here is the passband. And in the passband, we will have 1 by square root of 2 times whatever the maximum value of our transfer function is. And that is also just 0.707 times max, all right? So that is the idea of a passband and the 3 dB slash cutoff frequency. Going back to the transfer function, say h dot. So this will typically be in the form of a product of factors in, well, in this case, in factors in dot, since this is our arbitrary function, divided by another product of factors in dot. Putting the transfer function in this form will allow us to extract zeros from the numerator and poles from the denominator. And take, for example, h of s equal to s plus 1 times s plus 2 divided by s. So in this case, you can see that our zeros are s equals -1 and s is equal to -2, and our pole is just s is equal to 0. So whenever we take some s in the set of zeros, this implies that h of dot, or I guess in this case h of s, will equal 0. And then whenever we take s in the set of poles, that is, we evaluate our transfer function where S is at S of a value of a pole. So in this case, S equals 0, then our transfer function approaches infinity, right? Okay, moving right along. So we have the idea of a magnitude response. So a magnitude response, or I guess just the magnitude of h dot. So you take the numerator, take the real part of the numerator squared, add the complex part of the numerator squared, divide by the real part of the denominator squared, plus the real part of the, complex part of the denominator squared, and you take the square root of that. And that's just how the magnitude is defined. And then as for the angle, we take the tangent inverse of the complex part of the numerator divided by the real part of the numerator. It's not an R. Tangent inverse of that minus the tangent inverse of the complex part of the denominator divided by the real part of the denominator. That is how you will be able to find the magnitude and the angle of your transfer function. In the next video, I will go over some examples of how you can use this to find the transfer function, magnitude, and angle of a low-pass filter. Hope to see you there.